I realized I'm going to say this a couple times while people start joining, but I realized in the last two videos for moments, oh, hey, Mom. I noticed in the last two video for moments, I spent a lot of time talking about pretty abstract statistical connections between moments in physics and moments in statistics. And I didn't do really any examples, which probably defeats the purpose a little bit. Makes making this video series kind of counterproductive if we don't have intuitive examples to hold on to. So I figured I would do a little example on a live stream showing how moments of inertia, if you change the mass distribution a little bit, if you spread the mass out, which in the last video we showed that should increase the moment of inertia. We'll do a little example of two pretty similar mass distributions, only difference being mass more or less spread out, and we'll see how that affects the moment of inertia. And I also don't like memorizing things, so instead of just trying to memorize moments of inertia or anything like that, we're going to start with something much more general, the inertia tensor, and just to get people familiar with working with that. I got a lot of shit on my plate these next couple of weeks, so I wanted to make this just a live stream instead of a video, so I'm still putting stuff out every week. But yeah, let's go ahead and get started. What time is it there? I'm going to be looking at the chat throughout in case there's questions and whatnot. But to reiterate, we're going to do an example of seeing how moments of inertia change when we change the mass distribution. What I had in mind was, let me move this over maybe just a little bit. Just a little bit. It's cutting off. It's ruining the immersion of the stream. So let me move this over then. So what I had in mind was we'll start with one mass distribution where we have a thin spherical shell. So all of the mass is just spread over 4 pi on that boundary of the sphere. And we'll go ahead and say that the radius of that sphere is, RS for our shell. So RS means the radius of the shell, the spherical shell. And then we're going to compare that, we're going to calculate moments of inertia for that, and we're going to compare that against the moment of inertia of a smaller sphere of the same mass, where all of that mass is spread uniformly throughout the sphere. If you watched the video I made with Stephen Crocker, the physics of balls, where we talked about it was like that testicular cancer awareness video. This is basically the demo that we did. Was we rolled a spherical shell and then an actual smaller ball where it's the same mass, just more concentrated, and we saw which one hit the ground first when we rolled it down the incline. Now we're just going to sit down and we're going to do the math and see which one should win, and this should hopefully make it more clear why an object with mass farther spread out will have greater moment of inertia and therefore would require more torque to reach a given angular acceleration. So I've talked enough. Let's go ahead and define our stuff. This is RU for our uniform. And I'm going to insist that both of these spheres have the same mass, capital M. The only thing that's different is the density and the radius. So in this example, we're going to have that RS is greater than RU. The radius of the spherical shell, call this RU. I don't know why that gets canceled or cut out. Okay, same mass, different radiuses, different densities. Let's see which one should hit the ground first. Okay. So the way that I like to do this, I like to solve problems using as much of what's up here as I have, and I don't have a good memory, so I will memorize the more general abstract equation that covers more cases. That way I can treat all of these different cases as if they're really just the same problem. Rather than memorizing case 1 and case 2 and case 3, I start with something more robust that's maybe a little bit unnecessary for the particular problem. So it's kind of like scratching your left ear with your right hand, but we're going to get to the answer, and we're not going to have to memorize special cases to do so. And I think that that's what we should be encouraging physics students to do. Okay, so I'm going to start out with the definition of the inertia tensor. Now these are spheres. Spheres, This may be a shock to some of you, but spheres are spherically symmetric. That means whether I call this axis the z-axis, or if I start rotating about the y-axis or any other axis, physics can't tell the difference. Right? If you rotate a ball this way, it's just as hard as if I rotate it this way. Okay, so I don't care what you call your axis, we're just going to pick one and stick with it. So the definition of the inertia tensor, the ij component, is defined in terms of an integral over the mass distribution. So we're adding up all of the mass weighted by how far that mass is from the axis of rotation, which is defined by r squared delta ij minus xi xj. This is not, or this might have been one of the ways I wrote the inertia tensor in the last video, moments of mass distributions. But more often than not, what's expressed instead is the integral d3r times rho of r squared ij minus xi xj. The reason these two are the same is because density is mass over volume, right? So if I cross multiply, you get, and work infinitesimally, we get that dm is equal to rho d3r, the infinitesimal volume. You've probably, if you've seen the inertia tensor, you've probably seen it this way, which it's fine. It's confusing if this is your first time seeing it because it tells you nothing about what a smart choice of limits of integration should be, like when we actually do this integral. Whereas if we write it this way, we see we're adding up chunks of mass. So that tells us that the integral should stop where the mass stops. So that uniquely tells us where our limits of integration should end. If I just did this arbitrary spatial integral, that doesn't tell me that right away. Integrating the mass tells me, oh, okay, there's no need to go past where the mass is. Then I'm solving a different problem. Why the lined background, though? It helps me write straighter, you know, just like how you write on any other piece of paper. Okay, so in writing it this way, we see that the limits should end where the mass stops. Writing it this way, we know that it depends on the mass density. So eventually, we're going to have to write down the mass densities for these two different cases. So let's go ahead and get that knocked out right now. What do the off-diagonals mean? The off-diagonals are referred to as products of inertia, and it can mean one of two things. It can mean that the angular momentum isn't pointing in the direction of the angular velocity, which will resort in, which means you're forcing, like, say, the tires to rotate about an axis that isn't the principal axis, which will induce like kind of like a restoring force that gets you to wobble a bit when you're driving. And those non-zero off-diagonal components are would describe that. If that's not the case, it could just be that you're solving the problem in a stupid basis, like you're not solving it in the smartest coordinate system. So off-diagonal components are a little bit tricky to interpret because it could be that the physics is wonky, or it could be that you're not solving it in a smart way. So it's a little tricky. But let's start by, I'm gonna call this one, I don't know, system 1, and this one will be system 2. So again, for those of you who are just joining, these two balls have the same mass. The difference is how that mass is distributed. This one has a larger radius, and all of that mass is smeared along this thin spherical shell, where we'll assume the shell is infinitesimally thin. And this one is uniformly distributed throughout the entirety of the sphere, which has a smaller radius. So I'm saying the radius of the shell is larger than the radius of the uniformly distributed sphere. So how can we write out the density? This is also just kind of introducing you to how I go about solving these kinds of problems, because I think you'll notice that I tend to not treat things as special cases ever. I treat everything as if it's all the same problem. So whether I'm starting with a point mass, a linear charge density, a surface charge density, or whatever, I kind of pretend that it's a three-dimensional density anyways. And I let the physics tell me things can be simpler. So Like for example, here we have mass that's spread over the shell. So it's a surface charge, or it's a surface mass density, right? It's not really a three-dimensional density, but we can write it as a three-dimensional density where one of those density components is going to be a delta function. So if I say R1, the density, the three-dimensional mass density for the spherical shell, well, what should that be? Well, first of all of the mass is located a distance rs away from the origin, right? It's located in distance rs, and then it's uniformly smeared over 4 pi. So we need something to say all of the mass is located at r equal to rs and nowhere else, which is screaming a delta function. So the first part, we're going to have it's equal to the mass times delta of r minus rs. And then we're also going to have the surface density. So we're going to have sigma here. Actually, let's get rid of the m here. I'll contain that in the surface density. So if we call it sigma, which is the typical notation for surface densities, it's uniformly distributed, so it's mass per unit surface area. And what's the surface area of a sphere? It's 4 pi r squared. So this is just equal to delta r minus rs times that surface density, which is the mass divided by the surface area, which is 4 pi rs squared. Okay. So for those of you joining, we're starting with these two different cases of mass distributions for different spherical distributions, writing down the inertia tensor and translating these mass densities right away so that we know what we're going to be plugging in. Okay, so that's the first one. Let me see if there's anything crazy going on so far. I tend to make mistakes when I write and speak. Okay, I'll get back to one of these questions. Someone was asking about the variables with the different indices. If I have like I, j, I and j, I don't like, yellow is the punchline color. I and j are either 1, 2, or 3. 1 equals x, 2 equals y, and 3 equals z. It's just a convenient way of indexing things so that I can write summations more efficiently. Or so if I write something like I, z, z, that's talking about the z component of the inertia tensor, which is saying it's the moment of inertia, it's how much the mass is spread out relative to the z-axis. So in the xy plane. That's how you would interpret that. Go watch my video that I made last week on moments of inertia of mass distributions. Okay. So now we've got that one. Now let's move on to the other one, which is going to be simpler. So you'll notice it's the long way around of defining this mass distribution, but it makes it so that I don't have to think about surface densities off the bat or linear or what. I just think of it immediately as three-dimensional, and then I just try to write down what I'm talking about. Like I know it's all located at this distance away, and the rest is smeared over 4 pi. I'm just saying what I mean. Now we want to do R2, or row 2. And this one's simpler because it's just a uniform sphere with all the mass distributed uniformly throughout RU. So the mass density is just going to be the total mass divided by the volume of that sphere. So again, it's going to be mass divided by the volume of that sphere, which is the mass divided by 4/3 pi RU cubed, or 3m over 4 pi RU cubed. Okay. So there's our two different mass densities. Some of you who are unfamiliar with delta functions might be screaming, these don't look like they have the same units, because I have a 1 over r squared here and a 1 over r cubed here. But remember that the delta function has units inverse to the integration measure. So if we're integrating over r, which has units of distance, then delta of r has units of 1 over distance. So this really does, these do have the same units. Okay, now that we've got our mass densities, we can just, that's kind of the hard part here. The hard part is just trying to figure out how do I parameterize the mass density. Now that we've done that, the rest is just doing the integral, or the integrals. So let's plug this in. So IZZ, or I33 for the first system is the integral d3r rho 1 of r, and it's about the z-axis. So if we look here, r squared is x squared plus y squared plus z squared. Let me not do that. That's just going to be confusing. Let me write out exactly what I mean here. Yeah, let's just do this. R squared. If I equals j, the Kronecker delta is 1. Kronecker delta is just the identity matrix, right? So r squared just gets multiplied by 1, and then we're saying we're picking out the 3 component. So that's x3, which is just z, and x3 again, which is just z again. So we get r squared minus z squared, which is equal to integral d3r rho 1 of r x squared plus y squared. Because r squared equals x squared plus y squared plus z squared. Is there a reason why they're upper indices? No, it doesn't matter for classical mechanics. That starts to make a difference for special relativity, when there's a difference between covariant and contravariant vectors. Here it's just, no, there's no difference. Good question, though. Getting old, you're telling me. Okay, what's next? So now let's actually substitute in our mass density. And everything here is just a constant that we can pull out of the integral. This is the only part that actually depends on an integration variable. So when we translate this, I'm just going to factor out that m over 4 pi rs squared integral phi goes from 0 to 2 pi, theta goes from 0 to pi, and r, well, r, it actually doesn't really matter what we put our integration over because we have a delta function that we're integrating. So let's just say that we're going to the radius of the sphere, 0 to rs. But like we've said in the last video, delta functions are integrals waiting to happen. They just fix the value of that parameter for you. Someone says they can't hear me. Is that me or them? I'm gonna assume it's them because no one else is saying anything. Okay, so then the remaining part, the remaining piece was that delta of r minus rs. Then we have r squared, or x squared plus y squared. Before we do that, what is that? So we know that x is equal to r sine theta cosine phi, and y is equal to r sine theta sine phi. So x squared plus y squared is just r squared sine squared theta. And also, let me put this in a little box. We also have that the integration measure d3r is just r squared sine theta dr d theta d phi. There's some noise. Okay. Okay. So let's substitute all this in. So instead of this x squared plus y squared, I'm just going to write r squared sine squared theta. So we get r squared sine squared theta. And then we also get all those other fun factors from the measure times another r squared sine theta dr d theta d phi. There's no phi dependence in this integral, so that's easy. There's also a delta function which makes the r integral easy because this just picks out the value of r equal to rs. That's what delta functions do. Remember, I'm going to erase this right after, but in case this is new to you, f of x delta of x minus a dx just gives you f of a. So in this case, we have like an f of r, if you like. So then we're just going to plug in r equal to rs. So it's just, instead of r to the fourth power that we're integrating, we're just going to substitute in r to the fourth equal r sub s to the fourth. Let's also do the angular or the phi integral as well immediately. Since there's no phi dependence, we just get 2 pi. So this gives us m over 4 pi, don't know what that is, 4 pi rs squared. Sorry, my handwriting's kind of deteriorating. I should slow down. We also get that factor of 4 pi, or 2 pi I mean, from the phi integral. We also get a factor of rs to the fourth from the r integral and the delta function. And we have one more integral, 0 to pi sine cubed of theta d theta. So we've done 2 of the 3 integrals. And integral of sine cubed from 0 to pi just gives an extra factor of 4/3. So the end result gives us m over 4 pi rs squared times 2 pi times rs to the fourth times 4/3. Let's see, which gives us the 4 pi cancels with the pi here in the 4. 2 factors of this cancel, so we just get an r squared. So this gives us, unless I've made a mistake anywhere, it should give us a 2/3 m rs squared. So this would be the moment of inertia for a thin spherical shell rotating about any of its axes that are passing through the center of mass. Someone check me on that to make sure that I'm actually saying that right, please. I would just double check that one. So that's what this is saying. We've calculated the moment of inertia for this one. This is saying, so if we say that torque is equal to the moment of inertia times the angular acceleration, it's saying that we would need exactly that much torque to reach the given angular acceleration, and the more the moment of inertia is, the more torque is required. Okay, so we're going to check this against the moment of inertia for the uniform sphere of a smaller radius but the same mass, and see if its moment of inertia is larger or smaller than this. And remember, in the last video, for moments of mass, we came to the conclusion that the moment of inertia talks about how much the mass is spread away from the axis of rotation. So in our mind, we already know statistically that the moment of inertia, the larger the object with the mass farther spread out should have the larger moment of inertia. And now we're checking that, basically. We know what the answer sort of should be qualitatively. We didn't know it was going to be 2/3 MRS squared, but we know that it should be larger than this one, and that's what we're checking. And it's also supposed to be getting y'all introduced to the inertia tensor so that you can finally stop memorizing moments of inertia and calculate them for yourselves. Okay. So let's go ahead and do this for the second case. So, I, z 2 is equal to, same deal, we have this three-dimensional integral, d3r rho 2 of r, same deal, we're just doing this about relative to the z-axis, so smearing in the xy plane, which means it's the x squared plus y squared still, nothing has changed, so we can just immediately write down the r to the fourth sine cubed of theta here, dr d theta d phi. Let me say exactly what I mean here. Where did this come from again? The r to the fourth sine cubed theta, we got one factor of r squared sine squared theta from the distance to the z-axis, x squared plus y squared. So that's where some of those factors come from. And then the remaining come from the r squared sine theta in the integration measure. So that's all that this is. This part is strictly this part times d3r. Now let's do the integral. This integral will be pretty easy because the density is just constant as well. So we can pull all of the density outside of the integral. So what is that? I'm just going to copy that. Okay, so this is equal to here's our rho times the integral. Phi goes from 0 to 2 pi. Theta goes from 0 to pi. What should the limits of integration be for this one? For the r integral. As we said at the beginning, the integral stops where the mass stops. Where does the mass stop? Well, you start at 0, you start at the origin, and you integrate out all the way to RU. So that's what our limit of integration is going to be. RU. Okay, we've already factored out the mass density, so now we just have this fun little integral, r to the fourth sine cubed theta dr d theta d phi. And we can do all of these right away. Maybe it's clearer to not do them all at once, though. So we'll just do the angular ones first. 3m over 4 pi ru cubed. The phi integral gives us a 2 pi. And like the previous example, the angular integral gives us a 4/3 times the remaining integral from 0 to ru of just r to the fourth dr. That one's easy enough to where even I can do that one. Okay, so that's just going to give us 3m over 4 pi ru cubed 2 pi 4/3 and then an ru to the fifth over 5. And if we let the dust settle, what happens? The pi cancels again, the 4 cancels again, the 3 cancels. So we get a 2/5 m ru squared. There we go. So let's compare this. Which one is larger, 2/3 or 2/5? 2/3, right? So what this is saying is that the uniformly distributed sphere, even though it had mass distributed all the way throughout the sphere, because it was more concentrated to the center of mass or the axis of rotation, it resulted in a smaller moment of inertia because the moment of inertia, or sorry, the mass is not that spread out from the axis of rotation compared to the thin spherical shell. Both of these have the same center of mass. It's like right there at the center. So the thin spherical shell has the mass spread at a farther distance, which is why the moment of inertia is larger than this one. And as a result, it would take more torque for this guy to reach the same angular acceleration as the solid uniform sphere, which is why the solid uniform sphere will roll to the ground faster than the thin spherical shell. And you could also be a little bit more quantitative, and you can say, at what point does the thin shell start to win? So you can say, oh, RU is greater than RS, but we could say at what point does RU get large enough to where it starts actually having a larger moment of inertia than the thin spherical shell. So you can play that game as well. So we just took what we said kind of qualitatively in the last video, and we're able to make a quantitative, I guess, prediction for the moments of inertia for these two different but very similar mass distributions.